Okay, so we're going to just walk through problems. First one people wanted to talk about was getting time without the quadratic, help on that. So this is usually used for those time in flight kinds of problems where we want to get t, we don't want to use the quadratic. We have vi, we have delta y, we have a. So in these instances, delta y is basically the distance it falls. Even though it goes a whole lot of places in the middle, that difference in its initial and final position is the delta y. So looking at this, and I'm just going to plug in made-up numbers. So we say that this thing is being launched from 2 meters off the ground. It's got an initial velocity of 5.3 meters per second squared. We want to know how long it's in the air. Well, we can use the quadratic, but we don't want to do that. So what if we had, yes, sir. I screwed up my units on velocity, so corrected. 5.3 meters per second. All right. If we had VF, this would be easy. If we knew at this point here what the final velocity of this object is, and we know its rate of acceleration, and we know its initial velocity, we could use VF equals VI plus A delta T, which is just simple and beautiful and elegant. That's lovely. And then we could solve for delta T by saying, well, VF minus VI divided by A equals delta T. But we don't have VF. Nope, we don't. Darn it. But if we have delta Y and A and VI, we can create an expression for VF that will then allow us to plug in. What do we have that connects VI, VF, A, delta Y? Well, VF squared, let me do this in red actually, because this is what we're going to plug in. Let me up the pen size. VF squared equals VI squared plus 2A delta Y. So VF equals plus or minus the square root of VI squared plus 2A delta Y, which means we can take this whole thing and jam it sideways into that equation, which isn't actually so terrible. And this is a strategy, it's a workaround that we do use sometimes in Chapter 3 when we get to the projectile motion problems. I'm going to rewrite that with the substitution in place. So I have plus or minus the square root of VI squared plus 2A delta Y minus VI over acceleration, which really isn't so terrible. Move that down to there. If you struggle with making sure you know where that radical ends, put the radical in parentheses. That's an easy fix if sloppiness is what holds you back. And this is all equal to delta T. At this point, let's just take a look at this real quick, because what we've just done is we've created an expression that now connects VI, oh, that was one of our original variables, A, oh, that was one of our original variables, Y, oh, that was one of our original variables, and there's A again. We just took two different equations and created something that connects the original four that we had. And basically what we did is we reinvented the wheel here, because we've basically reinvented the quadratic equation. However, we've done it in context. So we're all perfectly aware that when this should be plus or minus, we can actually just get rid of the plus, because we know in this case, looking at the situation, looking at the picture, we know that VF is going to be negative because this thing is plummeting back to Earth. So VF is going to be negative, so we can just put a negative in there and save ourselves the thinking at the end, because we know that that's going to be a negative number. Okay? So let's go ahead and we'll plug in our numbers and see what we get. Okay, so I did forget to make my delta Y negative in my list of variables. You got to make sure, because if you don't make it negative, what happens? Well, you end up with a negative under the radical, and everybody knows that goes nowhere good. So that's all. I'm going to wrap that just to not screw it up. Minus 5.3 meters per second squared, all over negative 9.81 meters per second squared. Let's calculate. Getting a raw number that looks like that? Okay. sig figs? 2, 5.9. So 5.9 seconds would be our delta T. Why would this be a good potato cannon problem? Here's why. If you have some idea of, let's say, the muzzle velocity of your potato cannon. So does everybody know what a potato cannon is? No? PVC pipe. Okay, piece of PVC pipe. Now, the most primitive versions are literally just a sealed off piece of PVC with a little tiny hole drilled here at the end, big enough to accept a stick lighter. In the most primitive iteration of this thing, you literally spray Aquanet, that's the hairspray, into the barrel of the cannon, filling it with fumes. You then jam a spud down into this end, and you stick a lighter in here, and it goes boom! And the potato goes flying out of the potato cannon at high velocity. We could totally do this. Oh my gosh, we should so do this. Anyway, but I'd make you do the chemistry too. I'd make you do the stoichiometry for sure. Which would mean we would have to figure out volumes of gases. We could do that though. We could do that. If you know the muzzle velocity, the VI on your potato. Now, only an idiot shoots straight up in the air, right? You've heard this? Have you heard this? Have you heard, and I'm not sure if they're urban legends or not, I'm going to leave it as that they're not. For many years I lived in the city of Youngstown, and in Youngstown, and in large urban areas in lots of places, and maybe in the valleys of southern Columbiana County as well, one way to celebrate New Year's is to fire your gun in the air. There's just one problem with that. What goes up must come down. And there are stories of people being hit by bullets that seem to fall out of the air as if by magic. Not good at all, because what do we know about the final velocity on that thing? It's going to be actually slightly higher than initial, because whatever initial velocity it took to get it to whatever height at a given rate of acceleration, it's going to return to Earth with that same distance over which to accelerate, and it's going to be going, at the point when it passes where it was discharged, it's going to be going at least as fast as it was at discharge. So it's pretty dangerous. What we could do with this calculation with a potato cannon is figure out how many seconds you have to get to cover. So if you're dumb enough to fire your potato cannon straight up in the air, how many seconds do you have to cover yourself? It's a practical application, I think, of the physics. Okay, does anybody want to go through one more of these? Are we good with this? 0 to 5. If you're being sneaky, you can like flash me little physics signs. Good? Okay. I forgot to unpause this. Okay, well, such is life. So now we've got plus 2 times negative 9.81 meters per second squared. That's a negative. Oh, negative 7.3 meters. That's another negative. Okay, so here, these are going to be fine because it's squared. Here we got a negative times a negative. That's going to be fine. But that's how many places we have to make potential mistakes. So that's a lot of places to make potential mistakes. Go ahead and get numbers. Anybody else got a number that looks something like that?
Yeah.
Negative 12.89, etc. So how many sig figs do we have? 2. So this should be negative 13 meters per second. Okay. Does that help?
Yeah.
Okay. And it's just paying attention because the sign is the proxy for direction. That's the whole thing. Okay, other questions, other things that you missed, etc.? So what I'm going to do is I'm going to float around and I'm going to sit down with folks and look at your FIP quiz and try to do error analysis with people if you haven't. So if you know that that's coming, basically if you got less than a 6 out of 8 on your FIP, I'm going to come to you and sit down with you and look at the error analysis. So I would have those out, and if you have already traced your error, that saves us both time. So try it. Start finding your errors. Actually, there was a physics teacher I met last year. I was on a state committee for physics curriculum. And like everybody there was way smarter than me. I spent the first day being very, very quiet because I was like, crap. They were fantastic. And the one woman said her physics tests, she gives back with no grades. She just circles where it went wrong because she wants to train her students. I mean, that's kind of what I do with the mistake game. She wants to just train them to look for where it went off the rails, which is a fantastic approach because when you're doing big problems, the big thing that you want is to learn how to identify where you fell off. So start looking for where you fell off. If you missed stuff, circle where you think the mistake happened, and I'll come around and help you confirm or deny.